Thermodynamics has a major application for generation of power. Most of the power plants, they are based on one or the other thermodynamic cycle. The cycle which uses vapor as working substance, that is known as vapor power cycle. The steam power plants are the most widely used power plants used around the world. These work on steam as working substance and they work on vapor power cycles. All coal based and nuclear power plants and power plants where process steam is required, they work on these thermodynamic cycles. The most efficient thermodynamic cycles are the reversible cycles, and Carnot cycle is one of the most efficient reversible cycles which have been discussed earlier, and it consists of two isothermal heat addition and rejection processes and two isentropic expansion and compression processes with vapor as a working fluid. The cycle has been shown on TS diagram for steam in the figure. The on TS axis, the cycle shown 1, 2, 3, 4 or 1 dash 2 dash 3 4 is the Carnot vapor cycle. In this 4 1 is isothermal heat addition process, 1 2 is isentropic expansion process, 2 3 is the isothermal heat rejection process, and 3 to 4 is isentropic compression process. The Carnot cycle is the most efficient cycle, being a reversible cycle. However, it is considered as a theoretical cycle, as it is not practical cycle for the reasons already discussed. They are the compression of very wet vapor is not practically possible. Here we see that the steam is being compressed from 3 to 4. At point 3, the steam is extremely wet and it consists of a small fraction in the vapor state and a major fraction in the liquid state, and to compress the liquid is not practical. Liquid being incompressible fluid cannot be compressed isothermally, and therefore, this process 3-4, the isentropic compression process, is not a practical process. Then 4 to 1, the heating process is isothermal as well as constant pressure, but 1 to 1 dash, the heating the isothermal heating superheating of steam is not possible, and superheating of steam isothermally is almost not possible, and therefore, also if saturated steam is expanded from 1 to 2, the wetness at point 2 is very high, and this wet steam will create lot of problems in the turbine, and therefore, this is again not a practical expansion process, and that makes the system not a practical system. It becomes an ideal system only, and certain modifications are needed to make this Carnot cycle a practical vapor cycle for steam power plants, and a practical vapor cycle. The changes that are required to be made is that the heat addition process has to be constant pressure in place of isothermal process, and heat rejection process has to be carried till the working fluid is fully converted into saturated liquid state. And if we make these modifications, the cycle becomes a Rankine cycle. Rankine cycle is the theoretical cycle for steam power plants, and it consists of the following processes. A Rankine cycle has been shown here. A Carnot cycle has been shown here. It consists of 4 major components: a boiler where heat is being supplied, a turbine where this heat energy is converted into work, a condenser where heat is rejected at a lower temperature to heat sink, and a pump where the pressure is raised. This pump replaces the compressor and work is being done in the turbine, and the cycle has been shown here for saturated as well as superheated steam. 4 to 1 or 1 dash is heat supplied, 2 dash to 3 is heat rejected, and 3 4 is the raising the pressure in the pump. This shows a Rankine cycle on TS and schematic diagrams. The steam is generated at constant pressure, heat is added to water from 4 to 1 or 1 dash. The constant pressure heat addition is partly at constant temperature and partly it is with rise in temperature. Then expansion of steam in turbine is considered as isentropic from 1 to 2 or 1 dash to 2 dash. Rejection of heat in the condenser is constant pressure and at constant temperature, as it is latent heat rejection, and this the latent heat rejection, the heat rejection process is fully isothermal, and 3 to 4 is the raising of pressure of water. This water being an incompressible fluid, the process can be considered as an isentropic process, but it is not a compression process, it is just an isentropic process to raise the pressure of the water. Now, this cycle can be analyzed assuming that 1 kg of fluid flows through the cycle. Then from the first law of thermodynamics, we can write that the heat supplied minus the work done is equal to change in enthalpy. All the components, though the cycle is a closed cycle, but each component is a open system. The boiler gets some water from the pump, and then that heat is heat is supplied to the boiler, and the steam leaves the boiler in the condition as shown here. At 4, water enters the boiler, and at 1 dash steam leaves the boiler, and in the process heat is being supplied from 0.4 to 0.1 dash, and the total heat supplied is equal to H 1 minus H F 4, that is the enthalpy at 0.1 and enthalpy at 4, difference of the two is the total heat supplied, and the heat rejected is from 2 dash to 3, that is H 2 minus H F 3. Work done in the turbine is the drop in enthalpy shown on the TS diagram. From 1 to 2 or 1 dash to 2 dash is the work done in the turbine, and work in compression work of pump is H F 4 minus H F 3. The net work done in the cycle is W T minus W P, work of turbine minus work consumed in the pump, that is H 2 H 1 minus H 2 minus H F 4 minus H F 3, and the efficiency, thermal efficiency of the cycle, Rankine cycle, would be the net work done divided by the net heat supplied, that is H 1 minus H 2 minus H F 4 minus H F 3 divided by H 1 minus H F 4, that is the heat supplied. The pump work is negligible as compared to turbine work, and it can be neglected, that is H F 4 minus H F 3 is negligible as compared to the amount of work done, and therefore, we can write H F 4 is equal to H F 3, and that is also equal to H F 2. H F 3 is equal to H F 2, and that is almost equal to H F 4, and therefore, the thermal efficiency can be rewritten as H 1 minus H 2 divided by H 1 minus H F 4. H F 4 being equal to H F 2, we can just write H 1 minus H 2 divided by H 1 minus H F 2. So, this is the thermal efficiency of the turbine, and it can be said that the net heat supplied is area under the curve. If we extend this, this is the total amount of heat supplied in the cycle. This area is the heat supplied, and this area is the work done in the turbine, and this is the amount of heat rejected in the condenser. So, this total area that is the heat supplied, and this is the this area represents the work done. So, this area divided by the total area is the efficiency of the Rankine cycle that can be computed, and it has been shown as area of T S diagram divided by the area of heat supplied. 1A, there is slight mistake. This area of T S diagram 1 2 3 4 1 divided by area 1 A B 3 1. It should be some typographical error is there, and efficiency has to be written as area 1 2 3 4 1 divided by area, this is A B 1 A B 3 1. So, that this correction has to be made on the slide, and this shows the efficiency of the Rankine cycle. Now, here we have seen that the efficiency has been defined, and this efficiency depends upon the operating parameters of the Rankine cycle. And to find out what are the parameters which would affect the Rankine cycle, let me again explain. The efficiency would be maximum when this area is maximum, work done is maximum, and heat rejected, that is the losses, are minimum. And to make this area maximum, this area has to be maximized, and if this area has to be maximized, this line should be as high as possible, this line should be as low as possible, and the diagram should be as wide as possible. So, that the area of the work done by the cycle, this area increases and the losses are minimized, and that has been that we can say that the performance would depend upon the inlet pressure, that is this line should be as high as possible. So, that the area under this curve is maximum, the width of the diagram should be as high as possible, or this line should shift as far as possible on this side, and therefore, the degree of superheat should be as high as possible, and the condensing pressure, this line should be at the lowest possible point, or the condensing pressure or the condensing temperature should be low, and that would maximize the performance of the Rankine cycle. We will study the effect of these parameters one by one. Let us study the effect of inlet pressure. We assume that the inlet temperature of the steam and exhaust pressure of the steam being same in the two cases, if the pressure is increased, we can see that the average temperature at which heat is supplied is higher if inlet pressure is higher. Initially, the cycle was 1, 2, 3 and 4. Now, the inlet pressure has been raised from pressure P 1 to pressure P 2, and therefore, the temperature of supply of heat also increases from T1 to T2. The maximum temperature in the two cycles keeping the same, that is T1 dash is equal to T1. We find that the steam that work done in this cycle increases by this area, whereas the loss in the work is given by this, and that shows that the total work done in the two cases is almost the same. Whatever is the gain in work done is equal to the loss in work done in the two systems, but the heat loss which was earlier from 2 to 3, now it is from 2 dash to 3, and therefore, there is a saving in the loss, rather less quantity of heat is being lost in the case when the temperature increases. In the new conditions, this is the loss in heat, whereas earlier the heat lost was given by this area. So, this net amount of heat has been saved in the condenser, and this saving would result in improving the efficiency, and therefore, if the inlet pressure increases keeping the temperature and the condenser pressure same, the efficiency of the Rankine cycle would increase. The another parameter is the effect of superheat. If the steam degree of superheat is increased as shown here, initially it was 1 2, and if the steam is heated from 1 to 1 dash, there is a net gain in work as shown by the hatched area here. At the same time, there is net loss of heat that increases in the condenser by 2 dash B dash 2. So, there is net increase in work and net loss in work, net increase in work at the cost of this small increase in heat rejection rate, but the rate at which work increases, this is very clear. The ratio of the two areas, the rate of increase of work is more than the heat that is being lost in the condenser, and therefore, the efficiency would increase if the temperature of superheated steam at inlet to the turbine increases. So, the net power of the plant will also increase and the efficiency will also increase. The steam will be drier at the end of the expansion process, and that would improve the working of the turbine also. So, we wish that the steam should be, the temperature of steam should be as high as possible. Then the third parameter which affects the performance is the condensing pressure. It has been shown that keeping the inlet pressure and temperature constant at 0.1, the condenser pressure is reduced from 2 to 2 dash, and if the condenser pressure is reduced from 2 to 2 dash, we find that this hatched area is the extra work that is available in the turbine, and that shows that the total work output of the turbine increases, the total loss of heat decreases by this area, and therefore, if the temperature of the turbine condenser temperature of the steam in condenser is reduced, the efficiency of the Rankine cycle would increase. So, this we can conclude that because of these three parameters, the pressure should be as high as possible. Pressure, boiler pressure, should be high, steam So, these are the three parameters which should be maintained as expressed here, but there is a limit by which these parameters are governed. We say that the pressure should be high, but we cannot keep it indefinitely high, because that is determined by the strength of the material that is being used, and we cannot go beyond a particular pressure determined by the properties of the material used for boilers and other components. The steam temperature should be high. The temperature is also determined by the metallurgical limits, and we cannot increase it beyond a particular level, and normally a temperature of 500 to 550 degrees centigrade is maintained at inlet to the turbine. So that the material for turbine and boiler, they do not lose their strength because of high temperatures, and the condenser pressure should be low. The condenser pressure is determined by the temperature at which heat is to be rejected. In normally, the temperature at which heat is being rejected in the condenser is the wet bulb temperature of the atmosphere, and we cannot go below the wet bulb temperature of the atmosphere for rejection of heat, and correspondingly the condenser pressure should be the saturation pressure at given wet bulb temperature, because that is the minimum temperature of cooling water that can be attained, and below that the temperature cannot be maintained. So, these are the three parameters which are governed by certain limits, and they should be maintained as high or as low as desired, as explained here. Then how the performance of Rankine cycle can be improved, and for that certain modifications have to be done. First of all, the reheat cycle can be made use of, and in reheat cycle has been shown here. It is desirable to admit steam at higher pressure in the turbine. However, if steam is admitted at very high pressure, that would result in low dryness fraction at outlet to the turbine, which is undesirable, and this can be controlled by admitting steam at a high temperature, and secondly tapping the steam in between the stages and expanding this steam in stages and heating the steam between the expansion stages. This process is known as reheating. The steam from the boiler goes to the turbine it expands in the turbine. Then at some point where steam starts becoming wet at point 2, it is sent back to a reheater. This is a reheater where the temperature of steam is again raised at constant pressure 2 to 3. Temperature T 3 is almost same as temperature T 1. Then 3 to 4, it again expands in the low pressure turbine. This is high pressure turbine, low pressure turbine, and from 4 to 5 the steam goes to the condenser where it loses heat. The advantage is that if the steam would have expanded from 1 to 2 dash in single stage, the steam would have been extremely wet, the drainage fraction would have been very low, and that creates problem in the turbine blades. And therefore, to avoid this problem and get more work, heat is being superheated again and expanded. So, that helps us in getting this much extra work in the turbine, low pressure turbine, whereas this much extra heat is to be rejected in the condenser. So, the total capacity of the plant in megawatts that increases, and the efficiency may increase or may remain same, or what is the total amount of increase in efficiency would depend upon the temperature and pressure at which steam is superheated. Normally, the efficiency of the steam and the total capacity of the plant would increase if steam is reheated, and number of stages are being employed in most of the power plants. A large number of stages are provided, so that the capacity of the plant increases, the efficiency of the plant also increases. And this reheat cycle has been shown here. The work done would be H 1 minus H 2 plus H 3 minus H 4. This is the total work done. Total work done is the area of the T S diagram. This is the extra work done, and the total work done would be given by this total area as shown here. And the heat supplied would now be from H 3 minus H 2 plus H 1 minus H F 5. H heat is being added from 6 to 1 and then 2 to 3. So, total heat supplied is H 3 minus H 2 plus H 1 minus H F 5, and therefore, the cycle efficiency would be H 1 minus H 2 plus H 3 minus H 4 divided by H 3 minus H 2 plus H 1 minus H F 5. Here the pump work has been neglected, but because this is negligible as compared to the work obtained in the turbine. In actual power plants, just to have an idea of what is the pump work as compared to turbine, in a 500 megawatt power plant, the pump consumes almost 1 megawatt. The feed pump consumes 1 megawatt of energy. Of course, 1 megawatt is a huge sum of energy that is being consumed by the feed pumps, but out of the total 500 megawatts generated, this 1 megawatt would be negligible, and we can neglect it because 500 minus 1, that is 499 megawatts is the total output of the turbine, and pump consumes only 2% of the total energy generated in the turbine, and that can be neglected to simplify the calculations. Then another method of improving the efficiency is regenerative cycle. In regenerative cycle, the heat losses are again reduced by employing a regenerative cycle. A regenerative cycle has been shown here. The condensate from the boiler is pumped to the boiler pressure, and then this is passed through the turbine casing in the direction opposite to the steam flow, as it has been shown here. Here this is the condenser pump, the pressure is raised, and this high pressure water is passed through the casing of the turbine, and there the exchange of heat takes place. Here it is the steam that is flowing through the turbine, this is the water flowing outside the casing, and therefore, there would be an interaction of heat between the steam and the feed water, and this feed water, after being heated, after getting heat, then passes on to the boiler, and steam comes back and it flows into the turbine. Here the temperature of the steam and temperature of the water would be almost same at every point. Say this is the turbine and turbine casing here. Steam enters here, it flows through this, water from the feed pump is coming, now, when the water is flowing in this direction and steam is flowing in this direction, there would be a thermal contact between the water and the steam, and the temperature at each section of the turbine would be same as the temperature of water. Temperature of steam here and temperature of water here would be the same. Temperature of steam here and temperature of water at this point would be the same. Temperature of steam here and temperature of water here would be the same, and therefore, the heat there would be almost same, and therefore, heat will flow from steam to the water at constant temperature. So, this heating process becomes almost isothermal in the turbine, and the expansion of steam, of course, it does not remain isentropic. This there also heat of loss of heat takes place, and the process on T s diagram can be shown like this. So, initially we had seen in a Rankine cycle, the heating takes place from this point to this point. Now, here heating is taking place in steps in the turbine casing only, and in the boiler heat is being supplied from this point to this point. So, this becomes isothermal heating process. The heat rejection takes place from this point to this point. This is again isothermal heat rejection process. This is the expansion process, and this expansion process is almost parallel to the heat addition process here, and therefore, the shape of this cycle is almost identical with the Carnot cycle. The efficiency of an ideal regenerative cycle would be same as the efficiency of a Carnot cycle, and by applying the principle of regeneration, we can improve the efficiency. This efficiency improves because the heat that would have been rejected from this point, initially the heat would have been rejected here in the condenser, but now because of this regeneration, heat rejected in condenser is from this point to this point only. So, we are saving in terms of rejected heat, and saving in terms of rejected heat means we are gaining in terms of heat supplied, and that improves the efficiency of a regenerative cycle, and in ideal case the regenerative cycle would have the same efficiency as that of a Carnot cycle. But again, there are certain problems in regenerative cycle. We find that the dryness fraction here at this point, after when the steam leaves the turbine, would be at 0.3 here, and at this point the steam becomes very wet, the dryness fraction is low, and low dryness fraction is not at all desirable in the steam turbines. It would affect the life of the blades and turbine rotor, and therefore, it is undesirable. So, we cannot go for this type of heating of feed water by regenerative cycle, and this has to be again made a practical cycle. The difference in temperature of steam and feed water being very small, the heat transfer process can be assumed as isothermal process. Hence, it would be very close to a reversible process, and the efficiency of an ideal regenerative cycle will be equal to a Carnot cycle. However, practically it is not possible to have a heat exchanger in the turbine casing. Also, the steam in this case would be very wet at the turbine outlet, which is undesirable, and therefore, some practical considerations have been used to make this cycle a practical cycle, and it has been shown in the slide here, the practical regenerative feed water heating. In this, instead of passing water through the steam turbine casing, some quantity of steam is bled, it is being extracted at various points during the expansion process, and this steam is used for heating the feed water in stages as shown here. Steam enters here in the turbine, it expands partially from point 1 to 2. At point 2, small fraction of steam is extracted and it is sent to the feed water heater as shown here. And then the remaining steam expands from 2 to 3, again small fraction M2 is taken out, that is used for heating the feed water in the feed water heater 1, and the remaining steam expands to the lowest pressure and then it goes to the condenser. The quantity of steam extracted here is M1, quantity of steam extracted here is M2, and the remaining quantity of steam 1 minus M1 minus M2 flows to the condenser. In the condenser, this quantity 1 minus M1 minus M2, the pressure is raised to the feed water heater pressure, and then it mixes with the steam coming here. So, this water when mixes with the steam here, this temperature of the water would increase, the steam will condense and temperature of the water would increase. This heated partially heated water then goes to the feed water pump 2, where again its temperature and pressure they are raised, pressure is raised, and this is mixed with steam coming here, and the temperature of this feed water would increase because of addition of steam here, and this finally heated feed water 1 kg of water then goes to the heat pump feed water pump 3, and it is pumped to the boiler. The cycle is shown on TS diagram here. 1 to 2 steam expands in this region, then at 2 this some quantity M1 is being extracted and mixed with feed water at 0.9. Then 2 to 3 expansion takes place for the remaining steam 1 minus M1 kg, M2 kg is taken out and mixed in the feed water, and the rest of the steam expands to the lowest pressure. So, that shows that this shows the TS regenerative feed water heating on TS diagram. The advantages of feed water heating are very clear, that can be seen on this diagram. This steam that has been extracted here, if it would have expanded to the lowest pressure, the effect would be that this heat that is being used for heating feed water and going back to the boiler would have been lost in the condenser. Let me explain it again. steam is expanding, 1 kg of steam is expanding from 1 to 2. At point 2, small fraction is taken out and the remaining 1 minus m 1 kg expands down to the second stage, and at 3 again m 2 kg is being taken out and the rest of the steam expands to the lowest stage. Now, this m 1 mixes with water coming from this side at 8. This steam and this water, when they mix together, the latent heat of steam would be supplied to the water, the temperature of the water would increase and this high temperature water would go to the boiler. Similarly, m 2 kg here, this would this m 2 kg of steam would lose its heat to the water coming from the earlier stage. Now, what is the effect of extracting this heat in between these stages? This steam, if it would have expanded to the lowest pressure, it would have done more work. M 1 would have done this much extra work, but at the same time it would have lost this much extra heat. Now, this steam M 1 has done certain amount of work, but the loss has been reduced to 0, because this M 1 is being sent back to the boiler by mixing into the water, and when the loss has been reduced for this m 1 kg to 0, whatever is the work that is being done by this m 1 kg during process 1 2 is a net gain, and therefore, if work for this steam has the loss for this steam has been reduced to 0, that adds to the efficiency of the turbine, though the net work done in the cycle may be slightly less, because it is not expanding to the lowest pressure, but the loss is also being reduced, and reducing the losses is more important than the work that is being lost, and that is how by saving the loss here at this point, we can improve the efficiency of the turbine. Per kg of steam, the power generated may be slightly less in this case as compared to a normal Rankine cycle, but definitely the efficiency of the Rankine cycle would improve if we provide regenerative feed water heating using this particular cycle. The analysis has been done here. The work done in the turbine has been shown as H 2 minus H 1 in the first stage, plus in the second stage the quantity of steam is 1 minus m 1 kg. So, 1 minus m 1 into H 2 minus H 3, and in this third stage this is the total amount of steam flowing multiplied by H 3 minus H 4. So, the total work done in the turbine is given by this expression. Heat supplied is H 1 minus H 9. Heat is being supplied from this point to this point. In a Rankine cycle, heat would have been supplied from 1 to 5. 5 to 1 was the heat supplied. Here the external quantity of heat supplied is 1 to 9 only. So, that saves the quantity of heat supplied, and the loss of work, that is loss of heat in the condenser is 1 minus m 1 minus m 2 into H 4 minus H f 5. The heat rejected is this H 4 minus H f 5, and therefore, the cycle efficiency is the work done divided by the heat supplied, that is H 2 minus H 1 plus 1 minus m 1 H 2 minus H 3 plus 1 minus m 1 minus m 2 H 3 minus H 4 divided by H 1 minus H f 9. Now, how to find out m 1 and m 2? That can be found out by making the mass balance as well as energy balance at the feed water heaters. Say feed water heater here m 1 H 2, here in this case feed water heater 2, this is the m 1 quantity of steam entering to the feed water, and the quantity of water coming here is 1 minus m 1 at 0.8. So, the total energy coming to the feed water heater is m 1 H 2 plus 1 minus m 1 into H 8, and that is equal to H 9 here. Make an energy balance for this feed water heater. The total heat coming in is equal to total heat going out, and that gives us m 1 equal to this. and similarly M2 can be found out by making heat balance on this feed water heater, and that would be given by this expression, and this will be equal to this. The enthalpies can be read from the molecular chart, and that would give us the quantity of M1 and M2, and thus the efficiency can be calculated by substituting the values of M1, M2 and other enthalpies in this equation. The cycle efficiency can be found out. Here, what is the advantage that is clear from this diagram as shown here. Now, the diagram that is based TS diagram is for 1 kg of steam, and out of this M1 kg goes here, M2 kg goes here, but the quantities enthalpies given here are for 1 kg. These are the specific enthalpies, and to find out the quantity of work that is being lost because of this regenerative feed heating is that this area has to be subtracted. This area corresponds to the heat to the mass that is being extracted. This is M1 and this quantity is 2 to 9 is for 1 kg. So, this line has to be reduced in the ratio of 1 by M1, and this ratio is to be reduced by ratio 1 by M2. So, that this is the net work done per kg of steam in the regenerative cycle. This is the amount of work done per kg now, and this is the loss because of this heat that the steam that has been bled here. This is the amount of work that is being lost because of the steam bled here, and this is the net amount of work that is available on TS diagram because of the regenerative cycle per kg of steam. So, this shows the quantitatively what is the amount of work that is being lost and what is the net amount of gain of work in the turbine and this diagram shows that if we can just in large number of stages, this area can be drawn by this line can represent the expansion process in a regenerative feed water heating, and this shows that the actual practical regenerative feed water heating, the area is like this, and this is almost same as the area of a Carnot cycle. So, when large number of stages are being used, a regenerative feed water heating cycle will have almost the same area as that of a that of a Carnot cycle as has been shown here, and therefore, the efficiency of regenerative feed water heating cycle would be very large as compared to Rankine cycle. Then regenerative feed water heating cycle can be now combined with a reheat cycle, so that the dryness fraction does not drop at the end of the expansion process, and that has been shown here. This is the low pressure turbine, this is the high pressure turbine. This is the high pressure turbine and this is the low pressure turbine. The steam expands in the high pressure turbine, it goes for reheating, and again after first expansion at after 1 2, the steam is reheated to 0.3, and then again it is expanded to the lowest pressure. The steam is bled in several stages here, the first stage, second stage and the last stage, and that is the condenser pressure, and that shows that the cycle would be producing more power because of this reheat that has been provided here. And the analysis of the cycle has been done in the same way. We can find out the work done in turbine, heat supplied in the turbine, and the cycle efficiency. The values of M1 and M2 can be computed in the same way, and the performance can be found out. Now, the actual number of stages that are being used in normal power plants, very high pressures are being employed nowadays at the highest possible temperatures, as we have already discussed, and in that case the number of bled stages may be very large. Here just I have shown 3 stages, 2 bleedings, and finally the steam expands to the condenser. So, this is 2 feed water heaters only, but in normal practice where the pressures are very high, the temperatures are also very high, number of reheat stages are more, then the number of feed water heaters that can be employed, the number of stages that can be employed may range up to 9, 8, 9 or 10, and in that case you can just imagine what is the efficiency of such a cycle. This cycle would be a very efficient cycle in that case, because large number of feed water heaters being employed. Just to simplify the system, I have not shown large number of stages, but the basic concept has been explained, and that would help you to find out the performance of a reheat cycle along with regeneration. Thank you.